So Dalton didn't know much about atoms. Okay, think about what he used to figure out that there were atoms. All he used was the weight of elements and compounds. The only way he could explain why compounds always got the same ratio of elements. And if you had two compounds, the ratio in one compound compared to the ratio in the other compound was a whole number ratio. The only way he could explain that was that there were little tiny indivisible pieces called atoms. Not invisible, indivisible. They couldn't be cut. And if you can't cut them, there's nothing smaller. Okay? So Dalton thought of atoms as indivisible. Sorry, I had to let somebody in. So I thought of them as indivisible, and the only thing he knew about them was that this atom weighed different than that atom. That an atom of iron weighed different than an atom of sodium. That's all he knew. Okay? So he thought of them as indestructible spheres that weighed different amounts. And while that would explain the mass relationships, it didn't explain chemistry. It didn't explain why this reacted with that. So we had a lot more to learn about the atom, and we're going to start getting towards that today. So, parts of atoms. Dalton was wrong. Okay? He said that the smallest thing was an atom, and there are things smaller than an atom. So the next person on our list is J.J. Thomson. I think J.J. is John Joseph. Okay. So he's an English physicist, and that's actually pretty important. He's a physicist. He's not a chemist. Okay? And if you look at the time, it's 1897 is when they give him credit for doing this work. A couple things about 1897. Let's think about our time scale. Democritus came up with the idea in early BC. Then in the late 1500s, they redefined element and they created science. Late 1700s, about the time of our revolution, that's when Dalton came up with the idea of atoms. And then we got over 100 years before the next person on our hit parade comes along, and there's nobody in between. Okay? So J.J. Thomson, and he was trying to explain how a cathode ray tube worked. Okay? Cathode ray tube. So let me tell you what a cathode ray tube is. Now, he is not the first one to make a cathode ray tube. Lots of people made them, and nobody knew why they worked. So he was trying to figure out why they worked. So you start out with a glass tube, and then you suck all the air out of it. That makes it a vacuum tube. Okay? Vacuum. Because I spelled it wrong for 25 years, that's the right way to spell vacuum. That's one C and two U's. It's the only word I know that has a double U in it. But okay, all the air's been pumped out. Okay, and then they put a little bit of other gases are put in. So we got a glass tube full with a little bit of gas, and there's two metal discs. And I want to show you a video of what they were trying to explain.
A cathode.
Yeah. See if I can share that with you. Ooh. So this is a cathode ray tube. Okay. There's an electrode here, electrode there. They put in a piece of paper covered with phosphorus because when charged pieces hit phosphorus, it glows, so they can actually see where the ray is coming from. This end is called the cathode. There's a ray that comes off of it, and it's inside a tube, so they call it a cathode ray tube. The shorthand for that is CRT, which is what the old computer monitors and the old televisions used to use. The old television computer monitors were just cathode ray tubes. So this is how it behaves. Okay, you can tell that the ray is coming off here because this doesn't move, and as that magnet moves around, you'll watch the beam bend. And the magnet bends the beam. So this is what he's trying to explain. He's trying to explain why this is happening. What could make that happen? That's the device he's trying to explain. Oops. Okay. They also knew more about it. Okay. This is the same kind of tube. I know it doesn't look like it, but it is the same kind of tube. They just put a wheel inside. So this wheel is spinning. Okay. And the wheel is spinning because we've got a battery. Here's our tube, and there's the two electrodes, but notice they put the electrodes across the top so that anything that flies will hit that wheel and make it spin. So whatever is coming off this cathode is hitting that wheel and making it spin on its way to the other electrode. Okay? Because when you turn the power off, the wheel stops. You hook it back on, the wheel spins. So something has to be hitting the top of this to make it spin. So that told him that so before he started the experiment, he knew he could move the beam with a magnet, and he knew that the piece, whatever it was, had mass, that it was stuff. So he knew something with mass came off the cathode. Right? So we're back to this. So he knows that when he saw that when he turned the electricity on, the beam moved from the negative end to the positive end, and the negative end is called the cathode. The positive end is called the anode. Okay, the positive end is called the anode. And it came from the ray came from the cathode, went to the anode, so it's a cathode ray inside a tube. Now, you saw it move with magnets. Electric fields also do that. We can see that if you put the electric field, it turns toward the positive. Or you could say it turns away from the negative. So what's got to be true if it's it being pushed that way? Well, the rule is opposites attract. So this is being attracted, so if that's positive, this must be negative. Or we could also use the rule that same charges repel. So this is negative, this is being pushed away, so whatever there has got to be negative. So he knew moving pieces were negatively charged. Be okay at that? So now he knows he's got pieces with mass that have a negative charge. And he used lots of different metals and gases. Lots of them. And no matter what he put in that tube, the beam was always the same. No matter what he put in the tube, the beam never changed. Okay, by how much the beam turned, how much it bent, how fast it bent, he could find the ratio of charge to mass or mass to charge, doesn't matter which one, mass over charge or charge over mass. He couldn't find mass and he couldn't find charge, but he could find what the ratio was. Because if you think about turning something, if it's moving straight, you have to push on it. And there's two factors that influence how much it turns. One is how hard you push. So a bigger charge would push more, a smaller charge would push less. And the thing you're trying to turn, how heavy is it? Because heavy things are harder to turn than light things. So if I have something with a big charge and it's heavy, it's going to turn the same as something with a light charge, with a low charge that's light. So the ratio of the two is always the same. If you heavy over heavy gives you the same answer as light over light. Okay, so the heavy one is harder. Heavy with a high charge would look the same as light with a low charge. You can't tell the difference, but you can tell the ratio. And that's what was the same every time he did it. Let's see if I could show you that. On over, there we go. So here's actually what the equipment looked like. So he's got electrodes, he got his electrodes, okay? And there's the plates to do the electric charge, and he put magnets outside of it. So if you just turn it on, the beam goes straight through. But if you put in some E is for electricity, you put some charge down, I got a positive charge on the top and a negative on the bottom. Now when I play it, it turned towards the positive. And if I gave you more charge, it would turn more. And if you gave more charge, it would turn more. So the other piece he could do was he could, let's get back to play. So there's no charge. Remember, no charge is a straight line. Now B is how you measure magnetic fields. Okay. So the magnetic field, if you put a magnet on the outside of this, put a magnet on the outside of this magnet, turning up the magnet, bends it the other way. And the more magnet, the more it bends. So that by turning the electricity up, it turns up. Now if I turn the magnetism up at the same time, I can straighten it out some if I do it just right. I can get so the two cancel each other out. And with that, that's how it's by adjusting how hard the electricity over the magnetism that gave him something constant. So we said the ratio of charge to mass. Okay, so no matter how much electricity you put in there, no matter how much charge you put in, so he puts in a little charge. If you do all the math behind it, the ratio of charge to mass works out to be 1.73. If I turn the electricity up, put the charge up, the ratio of charge to mass is still 1.71. 1.7. It doesn't matter what value I turn this electricity into. It's going to turn enough so that the value works out to be about 1.71, 1.72. So we get that 1.7 for no matter what. So when we say the beam was always the same, and that he found the ratio of charge to mass, what we're saying is every metal he put in there, he got the same beam. Every gas he put in there, he got the same beam. It did not matter what he put in there, the beam always had that same ratio. And he had to try to, so he has got a whole bunch of observations about how cathode ray tubes work. Now he needs to explain them. Okay? How come it's the same with every material? Well, there's only one way, his only possible explanation. All right? If I have one element and a different element, they both give off negative pieces. That means that negative piece has to be in every kind of atom. Because if it doesn't matter what kind of atom you put there, you get the same piece. That means that piece is in every atom. And he published this paper saying that he had found a piece of the atom. And the chemist said, well, why would we listen to a physicist? He doesn't know what he's talking about. He doesn't know anything about chemistry. What does he know about atoms? He says, well, I don't know about atoms. I just take your word for them, that every atom for every kind of element. But when I put different elements in, I got the same piece out. So that same piece has to be in every element, and since every element is made up of atoms, it's got to be in every atom. So he found a small negative piece in everything, and that is we call it the electron. I think he called it the corpuscle. What's an E? Corpuscle. And so we did these experiments in 1897. He published his report, but it wasn't really widely accepted until about 1910, because the chemist didn't want to listen to a physicist. What does physicists know about atoms? Well, apparently he knew something nobody else knew. Now, he had a problem. He knew the atom was neutral, but he never found any positive pieces. So he got negative pieces, but you can't find positive pieces, but it's got to be neutral. So he had to change so Dalton thought we had this solid sphere that you couldn't break. Now Thomson says there's parts to it. Now you got to think about what the atom's going to look like with those parts. Well, he said it looks like plum pudding, which makes perfect sense if you lived in 1890s in Britain, because you would know what plum pudding is. I don't think any of you, I didn't know what plum pudding was until I looked it up. Plum pudding is raisin bread. Okay? It's not raisin bread. It's like raisin bread, except the bread is a spice cake like fruit cake. So you got a spiced cake with raisins in it. And the spice cake stuff, was the positive stuff. You had a big bunch of positive stuff that you couldn't separate. And then you had negative pieces that could go flying out, just like you could take the raisins out of raisin bread. Now, if we had invented this idea, we probably would have called it the chocolate chip cookie dough model, where the dough is the positive and the negative electrons are the chocolate chips that you could pull out of there. Okay? So that's what Thomson changed the view of the atom. Before it was just this indestructible sphere that weighed different amounts. Now it's it's not indestructible. It's got parts. It's still a sphere. Bunch of positive stuff with the electrons being able to remove. So that's what Thomson found. He found the electron. They wanted to know about how big the electrons were. How big is an electron? So we said they had the charge to mass ratio. There's the actual value right here. that if you take the mass of that electron and divide it by the charged electron, you're going to get 5.69 times 10 to the negative ninth. And the grams and the coulombs is a unit of charge, won't cancel out. So you'll have grams per coulomb. That's the number. So instead of that 1.7 that we got, because it was a different set of units, it's really 5.69 times 10 to the negative ninth. That's a tiny number. But what that tells me is, if I want to find the mass, dimensional analysis says I have got to multiply by something with charge on top. If I know the ratio of mass to charge, if I find mass, to find mass, I just need to measure the charge. So I need to find the charge on one electron. Not easy to do. And the person who figured it out that way, he did, unlike Thomson, Thomson wasn't looking for an electron. It's just the only explanation he could come up with. Millikan said, I want to find out about those electrons, so I am going to set up an experiment that will tell me about those electrons. It's a pretty complicated experiment in terms of all the pieces that go into it, but the idea behind it is pretty simple. So let's look at Millikan's experiment. Okay. This is a cutaway diagram. It's really a circular container with the pieces inside. On the outside, you've got some oil, fine motor oil or mineral oil, in a spray bottle. Back then they called it an atomizer because it tore it apart into little pieces. It's not into atoms, but so it's really just a perfume bottle. Squeeze the bottle, fine mist comes out. Those little particles of the oil are going to be so small that you're going to need a microscope to see them. And with a microscope, you can measure how big things are. You can measure things under the microscope. So he'll be able to see and measure the size of his oil drops inside the container. Inside the container, there are two metal plates, one on top, one on the bottom. The top one has a hole in it, right in the middle. The bottom one doesn't. So I cut it down the middle, there's a hole in the middle. So what's going to happen when you spray oil inside here? You're going to spray the oil and that fine mist, and a few of them are going to fall straight down through the hole. Those are the ones he wants. He set all of this up so he could get those oil drops to fall straight down. That was his whole, everything we've seen so far was so he could make oil drops fall straight down and see them. That's the whole purpose of everything we've done so far. Okay. Then, the reason why it's all in this container, is because the way that it's in this did all this inside that container is so he could shoot them with X-rays. So now he's got drops of oil falling straight down, getting hit with X-rays. He didn't know what X-rays were. That's why they're called X. But he did know that when an X-ray hit those oil drops, it would knock off some of the electrons. He couldn't control how many it knocked off, but he knew that that's what it would do. It would knock off electrons. So I got oil drops falling straight down, getting hit with X-rays, so the electrons get knocked off. So what am I going to be left with if I knock the electrons off of an oil drop? Well, as the oil drop falls and the X-ray hits it, the part that falls, the oil drop, gets a positive charge because the negative piece goes flying off. Okay, so everything. So now we've got it set up so that I have little tiny oil drops falling straight down with a positive charge. Okay. Then he put charges on the plates. That's why the metal plates are inside. He made the bottom one positive and the top one negative. So if this little drop with its positive charge is going to be pushed by the bottom and pulled by the top. Because opposites attract and likes repel. So he did all of this so he could get a drop of oil to be pushed up by charge, the force of the charge, and he could use that to fight the force of gravity. And if he did it just right, the drops would hover. That the force of gravity pulls it down, the force of the charge pushes it up, and they cancel each other out. He knows he can calculate the force of gravity. And if he knows this charge, the charge on the plates, he can figure out the charge on that piece. Because he knows the force has to equal the force. The force down has to equal the force up. The force up is caused by charges. If I know one charge, I can figure out what the other charge has to be in order for it to be that strong. Okay, so from the mass of the drop. Whoa, where did the mass of the drop come from? Well, he had a drop, he could measure its radius. And from its radius, he could find its volume. And that using density and volume, he could use that to find mass. You know how heavy it is, or you know how big it is, and you know how heavy it is for its size? You can figure out how heavy it is. If it's 2 grams for every milliliter, and you've got 20 milliliters, then you've got 40 milliliters worth of stuff. 2 grams for every milliliter times 40 milliliters gets me 80 grams worth of stuff. So that's how he calculated the mass of the drop. And he could dial the charge on the plates and measure that. And he calculated the charge on a droplet. Okay. Not on an electron. He didn't calculate the charge on an electron. He calculated the charge on the droplet. Okay. So what good did the charge on the droplet do him? So when he got the charge on the droplet, so he calculated the mass of the drop from the density and volume. He calculated the charge from the mass and the charge on the plates. Just said all those things. And when he got his numbers, there was a pattern. He didn't get the charge of an electron, but he got a pattern to his numbers. Now his numbers were much more complicated than this, but anybody notice anything about those numbers? What do those numbers all have in common? Well, what they all have in common is they're all divisible by 3. that for these, the greatest common factor is 3. They're all divisible by 3. So Millikan looked at the charges on the drops and looked at their greatest common factor. Because whatever charge he had on the drops had to be because it lost 1 electron, or 2, or 3, or 4, and whatever charge would be a multiple of the charge on the electron. So he found the greatest common factor, the charge on 1 electron, was 1.6 times 10 to the negative 19th coulombs. Everybody see why we had to learn scientific notation as we start talking about little tiny things? And once he knew that, he could calculate the charge of 1 electron and calculate the mass of 1 electron. So this is the charge on 1 electron. But remember this number from earlier, the ratio? If I take this many coulombs and multiply it by 5.69 times 9 grams for every coulomb, I will find that I have 9.11 times 10 to the negative 28th grams. And that is the mass of an electron. Electrons are tiny. And it's the mass of the electron. Give you an idea of how big this is, how small this is actually. Remember we said a raisin was about a gram? So if I took that raisin and I cut it into 1 billion pieces, and then I took one of those pieces and cut it into 1 billion pieces, then took one of those pieces and cut it into 1 billion pieces, it would still be bigger than an electron. Electron would be a little bit smaller than that. So electrons are tiny. So that's how they figured out that there were electrons, and how they figured out what electrons were like. Right? And that's what we want to focus on. And so that's why if you go to the module, you will see that I have put something called Thomson simulations there. And they're going to be simulations of the equipment that Thomson used. Simplified so you can focus on the important parts. Think about how charges would interact with each other and how masses would play a role in that. I'm going to put you into breakout rooms and walk through those simulations and answer the questions along the way. That make sense? Okay, so you're going to walk those simulations. You're done. I've talked to you about all this, so I'm going to have said everything that could be possibly an answer on that thing. Just see how the interactions show you those pieces. Okay? So that's what I need you to do today, is to do those Thomson simulations. So I'll put you in breakout rooms. If you got questions, you can message me from the breakout room. I'm going to pop in occasionally. If you find my name in your breakout room, that's because it assigns everybody, and since I'm in the room, it's going to assign me. So I can't do anything about that. All right? Any questions? No? Make sense? Okie dokie. So today you're going to do that. Then tomorrow I'll have you answer some questions about it to remind you about what Thomson learned. So you can there's some in the book about it. And then when we come back on Friday, we'll talk about the next part of the atom. Make sense? Yep. So we're off to the breakout rooms. Let's see. Is there anybody I need to move so that nobody's stuck with too few? Who am I? Nope, it looks like everybody's got at least 3. Okay, so there you go.